And while you are having your exam, I'm going to correct these errors. And meanwhile, I also work with this file. It's remove this thing here. Okay. I already showed you how, when you do a major calculation, you can save all the results in a binary file and then read it. So we already did the 1 plus 3 calculation. There are some error signs there that I will correct. And I will explain now, and probably I will need the blackboard as well, to show you how we have the 1 plus 3 system, and we transform the scalars into in terms of the Q scalars and fluctuations. We obtain a numerical system, a system that is easy to work numerically because the constraints are automatically satisfied, right? I made a notational change. Instead of psi 2, I'm writing the letter W. Okay, it's just notation because it's easier to remember W than psi 2 or something like that. So that's only a notational change. It's already implemented this correction in the other file. We'll have both files. The one we run before to generate the results with GR tensor, and the one that we're doing now. Okay? So restart, we read the falias, and we read the file that was created. So here are our names. It's Raichaduri, what happened? Raichaduri, energy conservation, shear propagation, W propagation. Now it's W instead of psi 2, okay? So shear constraints, W constraint. 1 plus 3 system for relativity models, all variables, etc. That's all the information. And it is also providing you the variables so that we can declare them with the falias. So now with the falias, we declare all this. Remember that Y is uppercase R, big R. I don't want to use big R because it might enter into conflict with the Riemann tensor, Ricci tensor, Ricci scalar, etc. Okay, so we run that. Well, anyway, just to show you the output of the falias. And here are the equations that we generate. Now there are some, have to check, these two equations have some problems with a sign that I have to check. I will do that, but it doesn't matter, it's not going to bother our lecture. But I will do that while you are suffering under the nasty exam that is coming on you.
Coming on you.
Right, you suffer there. I'm going to having coffee and
No, but we will not suffer, we will enjoy.
Okay. Masochist.
Huh? We will enjoy, we will think.
Ah, excellent. Okay. Okay, these are the now we declare, first thing we do to replace theta by h. Okay, so we declare the falias h, and everywhere we find theta we replace with 3h here, and just embellish.
So you don't need GR tensor now?
No more GR tensor. GR tensor
You don't need.
did his work.
Yeah. So
And in fact, these algebraic errors are not GR tensor, are mine.
Yeah.
So I'll have to correct them. Okay, then no more GR tensor.
No more, yeah.
Pure maple.
Pure tensor,
So we evaluate, we substitute this in all the equations. This is not, we did it in fact yesterday. So it's, we We do it in all the constraints, etc., and there's a summary. Now the equations look nicer because h is in one side, and the time derivatives are all in the left-hand side, etc. Right? So if you look at this system is very nice because it's self-contained. 4 unknowns, 4 equations, right? However, up to this point, we cannot just simply integrate it because we have to solve these constraints. We have to solve them. Now, these constraints, these are divergent. This comes from the divergence of the shear tensor and the divergence of the Weyl tensor, electric Weyl tensor. So these constraints involve the metric, see? You have this y prime divided by y. This are metric, involves both of the metric functions, right? The y prime and the y. So we cannot solve the 4 equations before solving the constraints. And here you can identify, for example, there is, up to this point, these equations are valid for any DOST solution. The DOST solution, or that is any DOST source for which, in which there is no rotation, right? There is no rotation, it's a DOST source, you would get these 4 equations here, right? So, where does spherical symmetry enter? Here. If we were working with some space-time that is not spherically symmetric, we would get here metric components that are non-spherical. It enters here. And even within spherical symmetry, see, okay, we say, no, spherically symmetric DOST solutions. So, even within them, solving these constraints is different for different classes. Like, for example, we can identify a subcase, a particular case of spherically symmetric DOST solutions in which this derivative, y prime, is 0. What would that mean? It would mean that this metric coefficient only depends on time. And this is a subcase of those solutions which generalizes Kantowski-Sachs models, right? And these are not LTV models, or you can say LTV KS models, whatever. But the models who are interested, the LTV models, this is non-zero. So you have to integrate these constraints. And these constraints are not easy to integrate, right? They can be integrated, but it's not easy. And if the cosmological constant different from 0, you can't integrate them analytically, okay? So the system is really not ready to work with it. So what we're going to do, and I'm doing it because I tried different ways, and it is easier this way. What we're going to do is the following. This is following. We have R, H, sigma, and W. Remember, W, psi 2. But to use the letter W. Okay? And we want to transform this system into rho Q, HQ, and I'm going to use these fluctuations, the relative ones, the dimensionless fluctuations, right? I'm going to use d rho and delta H. This is for convenience, but it doesn't matter because we already know that d rho is simply the simple fluctuation divided by rho Q, right? So it doesn't matter. We work with these ones, and we can also get the equations for these two, right? So what I did yesterday was not correct in the sense that if I simply substitute, make this substitution, right? I I didn't do this substitution. Well, this is identical to, if I make this substitution into the system, I don't get the right equations because I have to specify what are the properties of the raw cube. If I just, this is what I did was wrong. See? If I just plug this into the evolution equations for these ones, and then I'll make an algebraic, and solve the system algebraically, it's not the correct system because rho cube and H cube have special properties, right? They have special properties. So we're not going to do that. What we're going to do is we know that rho cube is rho q 0 by a cube, right? We also know that k cube is kq0 by a squared, and we already know that hq squared equals 8 pi 3 rho cube minus k cube, right? We know this, okay? So, and we also know that h cube is a dot by a. So from this information, we get immediately the evolution equations for rho cube and h cube. It's very simple. For example, what happens if we do this? What we obtain? We obtain, right? Hmm? Ah, yes, 3. Okay? So, but this is simply right? And therefore, we obtain very quickly, we obtain, this is the evolution law for rho cube, right? We have to specify that because we are doing this decomposition, but rho cube has special properties. It's not just something. It's like if I have this quantity, I can always say that this quantity is A plus B. This, to decompose this into a sum. But that's useless unless the things that are being summed have some special property. Otherwise, it has no information, no useful information. So here we are stating that this thing has this property, has this evolution law. Okay. Now let's work with this one here. This one, it says 2hq, hq dot is equal to 8 pi by 3 rho q dot minus kq dot. And we simply substitute. We simply substitute things. Like here, this would be equal to 8 pi by 3, that is multiplying minus 3 rho q hq, and we are adding this, which is simply, we can say, look, we can say that kq dot, well, let me write minus kq dot. Okay, so we have this. Now, kq dot is equal to minus 2 kq 0 aq dot, right? But this is nothing other than minus 2 kq hq. right? Right, you see this? Very simple derivative. So this thing then becomes equal to, here I can cancel the 3's, it's minus 8 pi rho q hq, right? Minus, but there is a minus here, so it's plus 2kq hq, right? So this is, so let's write this together. They're very simple. They're so simple that it's not even, it's a waste of time doing this on Maple. We do it directly here. So we have 2hq dot equals minus 8 pi rho p hq plus 2kq hq, right? So we see h is here, is here, is here, it goes away. Goes away. And then there is a factor 2, so we have hq dot equals minus 4 pi rho q plus the number 2 goes away plus kq, right? But we also know that kq can be obtained from here. We also know that kq is going to be 8 pi 3 rho q minus hq squared, right? So we just substitute all this. What we obtain is that this is minus 4 pi, and then plus 8 pi by 3, all multiplying rho q, right? Minus hq squared. And if we do this, this is this is minus 4 pi by 3 rho q minus hq. Okay, so we have the evolution laws for these two quantities. Okay. Now we're going to make the substitution, but we're going to say that these quantities have this evolution, right? Okay, and then we will find the fluctuations from the 1 plus 3 system. Okay, so what are the, as a summary, what we have is, we have this. We have rho equals rho q 1 plus delta rho, and we also have h equals hq 1 plus delta h, but we know that rho q dot was minus 3 rho q hq, and we also know that hq dot equals minus hq squared minus 4 times rho q. Okay? So this is what we're going to substitute. Obviously, once we dot, see, we're going to do this. Rho dot will be equal to rho q dot times 1 plus delta rho plus rho q delta rho dot, right? Okay? And we do all the algebra, you know, with with the equations, and we will get evolution equations for the deltas, right? And then the evolution equations for the deltas, together with these evolution equations, will be the evolution equations for the system. Okay? This is what we're going to do, right? This is the plan, and we're going to do it through Maple. But we're going to provide this input to Maple, right? Okay.
Excuse me, sir.
Yes.
So why do we need to derive this equation? Don't we get the same thing from the Rai-Chaudhuri's equation? It is the Rai-Chaudhuri form.
Yeah, but it's not the Rai-Chaudhuri form for the local variables. The local variables, see this, yeah, you recognize this is the Rai-Chaudhuri form for an FLRW. Except that, as I was telling you, the Q scalars mimic. They have the same properties as the FLRW scalars, except that they are LTV scalars. Because remember, the other one we have there, H dot, is different. H dot has this form. Right? It's not the same. Not the same. Because of this term here.
This term is not there in FLRW.
FLRW has just pressure.
FLRW would be this is not FLRW because HQ depends on PR. The FLRW would be this. But they depend only on time. Here we have constructed a scalar, HQ, rho Q, that satisfy the same equation, but they are not FLRW quantities. Yeah, okay? So be careful. The Rai-Chaudhuri equation for LTV models is this one, which is not the same. This would be the Rai-Chaudhuri equation for the Q scalars, which is identical to the FLRW, but except that it involves LTV scalars, right? Okay? Now, let's start mapling. Let's maple. So, first we introduce, say, rho Q, HQ, dm. dm is going to be going to stand for the fluctuation of rho. And in fact, maybe we can call it d rho. Yeah. D rho and dh, okay? These are, we're going to declare these variables, right? Okay? And then, we are also going to declare these quantities that we know. This is something that we know, but we know that the shear is essentially, see, don't get confused here. Remember that we're using the deltas, see? We already know that shear was minus dh, right? But this is the same as minus hq dh, right? Because dh is defined as the relative fluctuation, okay? Okay? Now, what we called before psi 2, we're calling now W, is minus 4/3 d rho, which is the same as minus 4 pi by 3 rho Q d rho. Okay? We know that from before. We will have to substitute. Okay? Now, first thing, so these are the substitutions. See here, let me write this comment. We introduce new variables, let's say the Q scalars and relative fluctuations. Okay. Here we introduce, okay, sigma and W in terms of the fluctuations. Here. And then what we're going to do, first we're going to look at the constraints. So what we do is substitute this form H. In fact, maybe we can, I'm going to simplify this. Okay. I'm going to introduce this. Say H will be H equals HQ times 1 plus DH. Okay, and then rho will be rho equals rho Q times 1 plus D rho. Okay, because we're going to be substituting these things. Okay, okay, we're going to be substituting. Now here we substitute first the equation for H in the shear constraint, right? And in fact, let me do this step by step, so that rather than let me do this step by step. First, we substitute the equation for H in the shear constraint. Okay. In fact, here, I want you to see first the constraint. This is step by step. This is a constraint, right? So first we substitute the equation for H. We're going to replace H in terms of HQ and the fluctuation, right? Here. Second thing, we're going to express sigma because sigma is also expressible in terms of the same variables, right? We get this. And then we also know, that the derivative of HQ, this we have seen in one of the properties of these things. This you have to remember. We saw this. We saw that for every Q scalar, the radial derivative is right. This is a property of the scalar. Okay, and we are writing this as this thing here is the same. This thing here is the same as the A, right? So this is a property of the derivatives of the scalars, right? It was explained, has been explained. If you don't remember, that's because you didn't study, but it has been explained, okay? Right? So we substitute this, okay? And then it's 0. So the constraint, this constraint is automatically satisfied. Once I substitute the new variables and the gradient, this gradient property, in fact, if you wish, we can even do something, we can simplify, we can define at this point to make it easier, see, gradient property, okay? Gradient property, we define it like this. We say, for example, the equation for HQR. Equation for HQR was HQR is equal to 3 times YR divided by Y multiplying HQ times DH, right? And we do the same for rho, see? I do this in order for you to have these equations there, so you can see them, right? We do the equation for rho QR, the rho QR equals rho Q d rho. Okay. So we have these two equations, or those equations, right? Now, here I simply substitute this equation, which has already been defined. That's the equation HQR. Okay? So I run the whole thing again. The shear constraint is this. We substitute the equation for H, we substitute the equation for sigma, and we substitute the equation for the gradient, right? And so the constraint is satisfied, right? Now let's do the same thing for the other constraint. In fact, okay. Rather than doing this thing in the same line, okay, let me do it like here. It's parallel to this, okay? So first, this is the W constraint. Move output from selection. Okay. This is the W constraint, right? Now, we substitute the equation for rho in the W constraint. Okay, we get this, right? Then we substitute the equation for W, we get this. And then we substitute the equation, the gradient, okay, we get 0. So this constraint is also satisfied, right? So two constraints are satisfied. So here we write something like the two constraints are automatically satisfied. Okay? So the 4 evolution equations can be treated as ODEs. Okay. Okay. However, we already know the evolution equations for rho, for, let me say, use this mathematical. Where it is here, H. We already know this the evolution equation, right? Yes. Therefore, what we need to find are evolution equations for the fluctuations. And this is what we are going to do, okay, for the fluctuations. Okay. So let's write the evolution equations for rho Q. So here it is equation rho QT, right? This equation will be rho QT, it's right there, equals -3 rho Q times h cubed, right? Okay, this is one of the equations over there. And we also have the equation HQT, right? This will be HQT equals minus HQ squared minus 4 pi 3 is kappa by 6 times rho cube. Right? So we already have these equations and we are going to put them inside. Right? Now, let's look at the equations that we have before. In fact, let me erase all this thing. We won't need this. So remove this so it doesn't make any noise. Okay. Okay. So we look at the evolution equations. Okay. The evolution equations, we have them here. The evolution equations are these four equations. So let's look at them. Let's have a look at them before we proceed. Okay. So notice the following. What we're going to do is the simplest of the equations is this one, right? Is the simplest of them. And in fact, this doesn't have shear or whatever. And then we're going to look at these two equations, right? And use these two equations to obtain the evolution equation for the deltas, for the perturbations, right? And then we substitute all this into these two and they should be identically satisfied, right? Now, because of an error sign or a sign that is not correct, they are not satisfied, but this is an error that has to be satisfied, that I have to correct, and I will report after your exam. But what we're going to do is we're going to substitute in these two equations, and it makes sense because the equations we have here are analogous to these ones, right? So we use these equations, we substitute here, and then we obtain the evolution equations for the delta rho and the delta H, right? And then we will have the complete system. Well, of course, provided these equations are satisfied. They are. Once we do that, these other two equations are identically satisfied. But I have an error sign, or a factor of 2, something that is not correct here that I have to check. Okay? So let's do this plan here. Okay? So here, comment, we substitute, and let me write exactly what we will substitute. We substitute rho equals rho cube times 1 plus delta rho, okay, and mathematical symbol here, and H equals H cube multiplying 1 plus delta, very good picture, right? To be able to, okay, substitute in the first two evolution, or let's say in the evolution equations for rho and H, rho and rho H. Okay, we do that. Okay, so what we need to do is we say eval subs. We're going to substitute the equation for rho, right? Which we have already defined here. That's the equation for rho here. This equation, this will substitute, first we substitute this, right? This is the whole things that we're going to substitute. Equation A, equation, all these equations, see? Equation for rho, where in the equation for rho t, right? So first substitute this. Notice how this has transformed. Now we have an equation for rho qt and for d rho t, but we already also have an equation for rho qt, right? So we substitute that. This eval substitute the equation for rho qt, right, above. Okay. Now this is it's done, right? And what we need now to substitute is for h. We have also an equation for h.
Sir, after eval and at the end there is a space. Is space matters or not?
No, it doesn't matter. Doesn't matter. So, here, you mean here. Yeah, it doesn't matter. And now we have to substitute the form. In fact, we couldn't have done this before. Like, also substitute the equation. Let's do this better like this, okay? Right? And now we substitute the equation. And if you notice, now there's all the new variables are there. All variables have gone, right? And so what we do now is to solve this for d rho, right? And we have for d rho t, right? So we do d rho t. See this fellow here, right here. This is what we are interested in. We want to see this thing, right? Okay. So say this equals solve, okay, the above thing for this equation, for this term, right? And that's it. This is the, and then we can even ask Maple to factor it. And this is the evolution equation for d rho. It's this one. And it's correct. I know it's correct because I've used it, right? So we call this equation d rho t. Okay. In fact, we can probably do something like this. Okay, so we have it. So now let's do the same thing with the Raychaudhuri type of equation, the Raychaudhuri equation for the Q scalar, for the scalars. So essentially, it's very similar, but we substitute these things here, right? Okay. Now what we need to substitute is the equation for HQ. It's the same, it's exactly a parallel form. Okay? And then we also need to eliminate the sigma thing, right? But we can do this by, in fact, we could have probably put the sigma here, eliminate the sigma here at this stage. See? There are no more old variables. All the variables have been eliminated. Then we replace the evolution equation for HQ. We put it here. And now we are ready to solve the system. Say DH, we need to solve for this one here. We're interested in this. So DHT equals solve the above thing for DHT. Yeah, that's it. But we can ask Maple to do some simplifications at the left-hand side of the above. Notice that rho Q appears in, that we can like factorize this in terms of, we can collect this, for example, collect in the right-hand side. We can collect the right-hand side in terms of rho Q and HQ. Let's see what we get. We get this thing. In fact, we can ask to collect also in terms of kappa, see, because kappa, we get this thing. This is and we can ask Maple to factor the terms. So this is the equation for DH, right? This is the equation for DH, and so we store it. We call this will be equation. We give it a similar name. Equation for the HT. So this is what we have. We have the equation for rho QT. We have the equation for HQT. And then we have these two equations. These are the equations that determine the system. These are the differential equations that we need to solve. Okay? And since the constraints are satisfied, then we treat them as ordinary differential equations, right? They only involve time derivatives, right? Now, what we still need to do is to check that the other two evolution equations are also satisfied, right? And you'll see how some that we don't get 0 equal to 0. There are some terms here, but this is because of an error. Nevertheless, we write here the following comment. We still need to check if the other two evolution equations for W and sigma. Where is the sigma here? And sigma. Are satisfied. Okay, so how do we check that? Let's look at these two equations. These are the equations for, let me lift this thing here. Okay. These are the equation, it was sigma T and equation WT. Okay. We have to see if these are satisfied. So we make the substitutions, right? First, we take the first one. Okay. First. Now, substitute. We have eval subs. First, we eliminate with x sigma to get rid of sigma. Then x h to get rid of h. Then, what else we need? And x, we have some x w. Okay, and we substitute all this in the equation for sigma. Okay, here. But we also have evolution equations for HQ and DH. So, sorry. So we substitute them. we have an equation, H QT, and we also have an equation, DHT, right? I think it was called like this. It was called like this. Yeah, DHT. Okay. So we have to substitute this thing in above. Okay. And then there are no more derivatives, and there are all the variables. So what we do is expand left-hand side of the above thing minus right-hand side of the above thing. This should give 0, but it doesn't give 0. There is an error here. So, but once corrected this error, it will give 0. Okay. Now the second one. Let's do the second one. Also has a problem. We substitute the second one. We also need to substitute all these things. To substitute a second one, what else? Equation sigma, equation W, equation H, and equation rho. Substitute in this area here. Okay, and then we substitute the equations for rho and the rho. It's a parallel process. And then, ideally, QHQ, these variables, and then we should get a 0 here, but we don't get a 0. Don't get a 0. Get some. Okay, this will be corrected, but it should give 0, right? Because, and then what we have is the system. The system, the 1 plus 3 system is now replaced by the other one we saw. See? So we make this comment now. The 1 plus 3 system is now replaced by these equations that I wrote here. Fine. Let me remove this thing here. 1 plus 3 system. It's replaced by this system. These are the new evolution equations, right? That have to be satisfied. And let me, it is very easy to pass these equations in terms of the other fluctuations, not the deltas, but the d's. Very easy. It's just a matter of substitution, right? So we'll do that. This is one way. So these are, so by evolution equations for, and here we say mathematics for rho Q, H, Q, delta, rho, delta rho, comma, and delta. These are the equations. But we can easily transform these equations for equations in terms of the others. Let me, once we have this equation, because the fluctuations are connected with each other, right? And then we also, as I mentioned before, we can also use the omega factors, the Q scalar omega factors, which I emphasize, they are not FLRW1. The Q scalar omega factors, we can also use them as variables, right? But let's now do with the
omega self.
Yeah.
Can't we solve this, these four equations simultaneously now?
Yeah, they have to be solved simultaneously.
Or
You mean solving one and the other and substitute the solutions, and yeah, that's also possible.
so we can have the answer now. So why? So we do need some more substitution for that.
Some more what?
Why are we introducing omega factors right now?
Sorry.
Why can't we solve the equations now and after that we introduce the omega factors?
Yeah, but that's more complicated. In general, say if lambda is different from 0, then these equations can be solved analytically. It can be solved as you say. You solve two of them first, especially the one that looks like energy balance, the rho Q, and the equation for HQ, which is a Raychaudhuri equation. You solve them analytically, and then you put the results in the other two, right? So that reduces the system to a system of two ordinary different. Yeah, it's possible to do that. But this is only possible if you can find analytic solutions for these two. And if lambda is different from 0, then you can't. Because notice that here I'm setting lambda equal to 0. What would happen if lambda is different from 0? If lambda is not 0, then we have an extra term here and an extra term here. We'll see that case also, right? We'll see that case. But in that case, what's the purpose of doing something numerical? Well, the purpose is that if cosmological constant is non-zero, then there is no point wasting time doing an analytical. Believe me, I've tried, because I have some knowledge on elliptic integrals. So I tried using Maple, and it's horrible. It's horrible. You get these horrible elliptic integrals, and they are very difficult to handle. So I dropped that. So when cosmological constant is non-zero, you go directly to numerics. Don't even bother doing anything analytic. Now, even when you can do analytic work, it is preferable to do simple, this is simple numerics. Come on, you just go to Maple, I'll show you. Go to Maple, write your 4 equations, and integrate them. You don't have to do a sophisticated program, Runge-Kuttra. This is done by Maple. See, this is done by Maple. This is like you want to make a phone call to Calcutta. You don't have to construct a telephone, right? You don't have to go and invent this, right? It's already invented, so you simply use it. It was a epopeic, heroic time for those who invented. And so say, bravo, bravo, bravo. And we remember the old days when you couldn't just call Calcutta or Mexico City. We remember these brave old days. But we use our cell phones. Right? So it's the same here. Maple and Mathematica allow you to treat this type of integrals very, very efficiently, right? So don't waste time on work. Well, if the problem is too simple, analytically, then it's justified. If analytic work is simple or is important, in some cases the analytic work is important. Case in point, if you study the asymptotic properties. Because if you study asymptotic means infinity, right? So numeric work doesn't like infinity, right? So if you are going to study asymptotic properties of these models, then analytic solutions are necessary, even if they are not exact, even if they are approximations, right? But asymptotic expansions and so on. So you need analytic forms. If you are going to do perturbations or something, then you might also work with analytically. But in many cases, it's just better to work these solutions numerically. Okay? So what we're going to do is First, I'm going to add two more equations to this system. Which equations? The ones that give us the metric functions, see? See, let me make this comment here. Okay. These equations determine the dynamics of LTV models. Like, once we solve these equations, how do we get not the quasi-local density, but the density itself? Well, we substitute, that's all. Because once we solve this system, we have rho q d rho h q dh. So we obtain rho simply by substitution, by evaluating this. We obtain h by evaluating this. We obtain sigma because we know that sigma is minus hq dh. And we know that phi 2 w is simply minus 4 pi. So we have everything. We have all the scalars that we need. The models are completely determined. But the metric functions themselves, how do we determine them? Well, we have to add the following equation. See, we know that HQ is A dot times A. And we know that DH is right? Sorry. Yeah, no, that's correct. But this is also DH. Therefore, we have A dot equals HQ A, and we have gamma dot equals 3 HQ delta H gamma. So these equations, we add them into the system, and we will also have the metric functions determined. So everything is determined, right? We have a system of 6 equations for 6 unknowns, and the whole system is the space-time is determined. So let me add this comment here. Yeah. To determine also the metric functions. Okay, what are the metric? Notice that the 1 plus 3 does not use metric functions only in the constraints, right? Right? The metric functions. Now notice also that this determines the metric functions A and gamma. So how you determine the metric functions of the standard? See, because we notice that we know if you have A, then you obtain R. See, you obtain R. You know, big R, which we are calling here Y. Big R is simply this, and R prime by R is simply this, right? So once you have A, you obtain R. And once you have gamma, you obtain R prime. Okay? So the metric functions A and gamma. Gamma is here. Yeah. So we declare them the alias ER, A, and I don't want to use the name gamma. Let me use this GG, because I can also not use, I don't want to use G because it's association with the Einstein tensor. So And what are these equations? We put them by hand. It's the equation for t, which be A equals AT equals A times HQ. The other one is the equation for gamma t, and it's simply JJT equals 3 times JJ times HQ times the H. So we add these two equations, and the system becomes completely determined. Even the metric functions, we get them as well. We get them in the same process, right? Okay? So it's very, very efficient. Now, let's see the system in terms of the fluctuations, the other fluctuations. And I think that like 10 more minutes, the other fluctuations, the D rho and the DH, right? Well, we have to simply express DH, the small d, see, ek rho. Let's write it like this. We don't have this name defined, so this would be d rho. First we have to declare them. With alias dr, and we declare them are going to be d rho and dh, right? In uppercase letters. So d rho is going to be simply d rho, capital letters, divided by rho cube, okay? And the same thing for the other one. H, dH equals dH by HQ. Okay? And we substitute, that's all. It's a matter of substitute. Now, the change, it will not affect the first two, because the first two have no fluctuations. That's another interesting point. Notice that these two equations have no fluctuations, only Q scalars, and are identical to FLRW equations, right? Now, here are the fluctuations. So, right from this moment, we can identify the dynamics of the models as composed of two parts. There are 4 equations that, well, let's say let's forget the equations for the metric. These 4 equations. There are 2 of them are the part of the dynamics of the models that has some touching point with FLRW, right? Say, yeah? And then the other part of the dynamics is the fluctuations that tell us the difference between the models and FLRW. And this is very similar to what happens in perturbation theory. Perturbation theory, the dynamics is decomposed in 2 parts. The background dynamics and the dynamics of the perturbations. Well, we have here something analogous. We can identify this as some sort of background equations, and this as perturbation equations. And it will turn out, we'll see that in future, I think in a couple of days, that actually these equations, these equations reproduce if we go to the linear limit, if we go to a linear limit, this becomes FLRW equations. And this becomes formally identical to linear perturbation equations of cosmological theory in the comoving gauge. We'll see that, because in perturbation theory, there are several gauges. Now here, because we're working in a comoving frame, we will reproduce the results of the comoving gauge, not the results of the longitudinal gauge or isocurvature. There are 1 million gauges, but those we're not going to reproduce. But the ones of comoving gauge, yes. So this is interesting because the dynamics of the models has two parts. So a part of the dynamics is identical to FLRW, and then there is another part which is different, but it will reduce to perturbation dynamics in the appropriate limit. Now, let's do this simplification. We only have to substitute in these equations, right? In this, we have to make the substitutions only here, right? Okay, say substitutions only in these equations. This equation. So let's start with the first one. We say eval subs. So we have to substitute this thing. And this thing here. Oh, stupid. And this thing here. Where? In this one. Right? And now we substitute rho qt. And then now, all what we do is to solve. It's d rho t equals solve the above thing for this quantity, for the desired quantity. That's it. That's our equation. We can even ask Maple to do some sort of collecting. Left-hand side above equals collect right-hand side. The above thing collected in terms of the rho. That's it. This is the equation. This is the equation, and we call this is the equation. It's called equation for d rho. Now let's do the same for the other equation. We substitute these things into the equation for dHt. We get this, and we need to do the equation for HQ. It's a matter of substitution. And then we just need to solve. And after solving, we do some arranging of terms. Right, so it simplifies very nicely. And we can say, something like, and a trick that I do a lot is this one. And then I want Maple to factor only these two things here. Okay, And then this will be the equation for DHT. And so this is, our system now looks like this. See? Summary. Okay. So these two equations, the first two equations here, we did not touch them, right? So they are the same. What we modified is this one, B, B. So this is our equation, and this is our system. Okay. We can add, for example, the equations for the these two. We add the equations for the metric functions. Okay. Notice also for the metric functions that this equation is common to FLRW, right? So in FLRW, you have an H and you have an A, but not this. This equation is not common to FLRW. So strictly speaking, we have three equations that are identical to FLRW, these three, and three equations that have no FLRW equivalent. Okay. So one, okay, so this is the system here. It's very easy to pass it from one to the other. Now, one question that people have not asked, where is the spatial curvature here? It's gone, huh? No spatial curvature. How can we compute the spatial curvature? How does this relate the spatial curvature with the density and with the Friedman equation, right? Because we've already seen things. I think people have not read the notes, or maybe Saturday you are like sort of lazy. Remember that we have this HQ squared equals 8 pi rho Q minus. We also have this thing. Okay, so once you know H and rho, you find KQ. Once you know DH and D rho, you find DK. This is how you find it, right? You don't need to compute them in the process. And this is important because given any two of rho Q, HQ, KQ, you can always find the third. Right? Given any of those three, two of them, you find always the third. If you have rho Q and KQ, you find H. If you have HQ and KQ, you find rho. Right? And the same thing here. Same for any two d rho, dh, k. Right? These two equations allow us, these two equations are telling us, these are constraints, algebraic constraints. They tell us that you only need two. You only need two q scalars and two fluctuations. Any combination of them, right? Any combination. So far, which combinations we have seen? We have seen rho q, hq, d rho, dh. We've also seen rho q, hq, d rho, and dh, right? So you're telling me, yes, but here rho h, rho h, rho h. No, not necessarily. We can work, for example, something like this: rho q, kq, and then dh, d rho. Right. These two different. Doesn't matter. You can always rewrite the system. We can rotate them. We can shuffle them around. You only need two of them. And you use these constraints to translate between one and the other. Right? Because you can always do that. You can always make the substitution. Suppose we want to use k as variable. What we need to do is to substitute, for example, here we have to eliminate h. We don't want to use h. We want to use k, kq. So what we do is we eliminate h in this term, square root of 8 pi 3 rho q minus kq. We do like this. We eliminate h. Now this is not very. It is possible to do, but it can have complications because this root, this square root, can have two signs. So have to be careful. That's why it's better. It's always safer to use rho and h rather than k. But it's also possible to do. You can also do this, right? Or suppose you want to eliminate, you can also do this. You can also do that. You can eliminate this rho q in terms of these two. And the same thing you can do with the fluctuations. You can shuffle around them. Right?
So let's say if we go by this method, we get two possible solutions, two possible sets of solution.
Mm-hmm.
So how do we eliminate the wrong one? How do we
No,
identify
none of them are wrong. No,
physically?
no, what might happen is that if what if you have a model that expands, bounces, and collapses? Then this is problematic because your h will have two signs. So you have to treat the problem in terms of an expanding branch where this square root is positive and a collapsing branch which is negative. So you would have to look at your system for each branch. That's a problem. It's like, for example, let me give you an example. Suppose this is the equation of the circle, right? Okay? This is the equation of the circle. Now, how can you describe this as a simple function? Because this is not a function, right? This is not a function. This is a constraint, really. But how do you transform it into a simple function? Well, you do this. But if you just do like this, then you are not describing the circle, but you are describing only this part, right? So, in order to get the full picture, you have to use two functions. You have to this decomposes into two functions, right? So maybe it's not convenient. It's not convenient to do this. maybe it's easier if you simply describe, if you use the parametric representation. See? You use a parametric representation. Because then in this case, a single expression, there are millions of examples in mathematics why some things are correct but are not comfortable. They put some computational difficulties, right? This is correct. This is the equation of the circle, right? But it requires two functions. The same thing would happen here. If you take this, you really would have to write h cubed equals plus minus. And well, if h is always positive, then that's it, no problem. But then that choice would not be very good if you want to study models that expand h positive, h cubed positive, and then collapse h cubed negative. So for these models, that's not a good idea. And it's the same thing that I mentioned yesterday, that why use the delta or the d? The delta can be problematic if the denominator becomes 0, which can also happen in bouncing models. So which combination of q scalars you use depends on the problem. Depends on the problem. The best one so far, the most practical one, is this one. This is so far, the most practical one is this one. This is the most practical one, this combination. Why? Because this one, the evolution equations for these two reduce to perturbations very nicely. Okay, so I think it's time to stop here and continue. Tomorrow we continue.